Okay, in this video, we are looking at electromagnetic induction. Now, let's see, electromagnetic induction, or simply magnetic induction, is a production of electromotive force across an electrical conductor in a changing magnetic field. Okay, so we discovered that when the magnetic field is changing, current can be induced in a wire. When you say induction, what does being induced mean? Being induction means the transfer of a characteristics without coming in contact. Okay. In this case now, it is current that is transferred to a wire, you know, by just moving or changing the motion of a magnet or the relative motion between a magnet and a coil. Now let's continue. It says this either happens when a conductor is set in a moving magnetic field, okay, when utilizing AC power source, or when a conductor is always moving in a stationary magnetic field. So here there are two ways that this can happen. It can happen this way, it can happen this way. Now for the case one here, you see a magnet changing direction, either entering or leaving the coil. But coming close or leaving the coil induces a current in the coil. You can see that the galvanometer is reading current to show that current is moving in the coil. This is amazing. This is an amazing discovery that magnetic field or a magnet with changing magnetic field can induce current in a coil. Okay, current can flow in a coil because of changing magnet. Now, but scientists also um, um, discovered that the reason is the change in flux density, and with that they can also achieve the change in flux density by allowing, that's in the case 2. Now you can see the first coil here has an AC current flowing through it, and AC current is an alternating current, meaning that the current is not flowing, the current flows periodically with time. Okay, it changes periodically with time. And remember that when current flows, it generates a magnetic field. So in this case now, as the current is changing, the magnetic field is changing. And because of the change in magnetic field, current can be induced in the second coil, which is this. How you know that current is induced is that the galvanometer will read that current has entered it. This is an amazing discovery in sciences. Okay, so now there are two persons that makes contribution here on the electromagnetic induction. The first one is the Faraday's law. Faraday. So the first law, Faraday gave two laws. The first law states that whenever a conductor is placed in a varying magnetic field, EMF is induced. Okay, I think we have seen that. When a conductor is placed in a varying magnetic field, as long as the magnetic field is changing, EMF will be induced. Then the second law states that the magnitude of the induced EMF is equal to the rate of change of flux linkages. Okay, so with that, you can see this formula here, that EMF is equal to, generally speaking, is N. N here stands for, of course, number of turns. Then this is the rate of change of flux to time, magnetic flux to time. Okay, and remember that magnetic flux is also equal to BA, that's magnetic field or magnetic flux density multiplied by area. Okay, if placed at an angle, it is going to be BA cos theta, just like we have here. Beautiful. Okay, so that now leads us to a second law here. The law is called Lenz's law. Okay, according to Lenz's law of electromagnetic induction states that when an EMF is induced according to Faraday's law, the polarity direction of the induced EMF is such that it opposes the cause of its production. So according to Lenz's law, you see EMF is minus. So the EMF here will be minus N, just negative, and the phi all over dt. Okay, so they all talk about the same thing. So length is actually concerned of in the direction of the induced current. Okay, so let's see certain questions here. Now the first one says the magnetic flux through a single wire loop changes from 3.5 Weber to 1.5 Weber in 2 seconds. The EMF induced in the loop is, now if you notice, nothing is said about the number of turns. So in that case, the number of turns is just 1. And it is already given, it says single wire loop, so just 1 times the change in the magnetic flux is 3.5 minus 1.5. Okay, now divided by the time here is 2 seconds. So 3.5 minus 1.5 is 2 over 2. So the answer is 1 volt. So the induced EMF here is 1 volt. This is beautiful. Now look at the second question. It says the magnetic flux phi in a coil 80 turns changes at the rate. Okay, they gave us the rate of change, which is 0.5 Weber per second square. Calculate the EMF induced in the coil. The EMF induced in the coil from what we have here is N times the phi over dt. Okay, that's the number of turns times the rate of change. Number of turns is 80 here. The rate of change is 0.5. Okay, so that is going to give us 40 volts. 40 volts. This is beautiful. Okay, now let's see for that of a solenoid. Now remember we said that, okay, let's read the question. A long solenoid is wound with 1000 turns per meter. Okay, that's the number of turns per minute length. The current in the windings is increased at a time rate of 100 amperes per second. That means time rate of current. The cross-sectional area of the solenoid is 40 centimeters square. Okay, calculate A, the flux in the solenoid, then B, the induced EMF. Well, the flux in the solenoid shouldn't be a problem. But before we can calculate the flux, not just the flux, that's the rate of change of flux, which is the phi over dt, can be calculated here. And in that case, we can use the formula. It is the BA all over dt, okay, which we can actually write as A dB all over dt. Okay, so we can know what the area is and know what dB over dt is. dB over dt is not a problem. If you notice here, B here is mu naught I Ni. So what will be dB over dt? Watch. It is going to give us mu naught N. Instead of I now, it will be di over dt. Why are we using di over dt? Because that is what we are given. We are given the time rate of current. Okay, so if we apply that formula now, my mu naught is 4 times 10 to the power minus 7, 4 pi, sorry. Okay, let me erase this part. Okay, so my mu naught is 4 pi times 10 to the power minus 7. Okay, now multiply by N is the number of turns per meter, which is 1000 from the question. Is 1000. Then times the rate of change of current, which is 100. So that gives us 100. Now that is that value is going to be if we have 4 pi times 1 so minus 7 times 1000 and times 100. Okay, that will give us 0.126. So that means the magnetic field is, or magnetic rate of change of magnetic flux is 0.126. That's dB over dt. So it's now easy to find the magnetic flux. So now let's go. So I can erase this. Now my magnetic flux, here we can say the rate of change of magnetic flux, because that is what we can do. The rate of change of flux, like we have seen here, is equal to A dB, okay, all over dt. So let's do that quickly. Your A is 4 area 4 centimeter square, which is 4 times 10 to the power minus 4 meters squared. If you convert that, then multiply by the rate of change of flux density is 0.126. Okay, so if we multiply that, 4 times 10 to the power minus 4 multiplied by 0.126, that will give us 0.0000504, or you say 5.04 times 10 to the power minus 5. Okay, now this is quite beautiful. This is beautiful. Okay, so in 1 second, the way we can leave our answer here, since we're asked to find flux, we can say in 1 second the flux is 0.0000504, or we can say 5.04 times 10 to the power minus 5. Now the next we are asked to find is the induced EMF. So what is induced EMF? Induced EMF, like we know, is N times the phi over dt. So our N here is 1000 tons, right? Then the rate of change of flux we just got is 5.04 times 10 to the power minus 5. So that will give us 5.04 times 10 to the power minus 2 volts, or 0.0504 volts. That is beautiful. Now let's see another question here. It says a magnetic field goes through a coil solenoid. The coil diameter is 2 centimeters. Okay. If the magnetic field goes from 0.02 to 0.01 Tesla in 34 seconds, what is the direction and magnitude of the induced current? Assume the current has a resistance of 0.1 amperes. Okay. Here we are asked to find the induced current. So if we know the induced EMF, we can find the induced current. That won't be a problem. Okay, so since we are dealing with a solenoid, first of all, what is B? We are already given, the file over the T, which is, it should be area times dP all over dt, based on what I've shown you before now. So the area is not given, but we know that area is pi d squared over 4 since diameter is given. Okay, so which is 3.142 times the d is 0.02, diameter is 0.02, that's 2 centimeters squared, divided by 4, and that will give us, if I say 3.142 times 0.02 divided by 0.02 squared, divided by 4, that will give us 3 times 3.14 times 10 to the power minus 4. Okay. So we have 3.14 times 10 to the power minus 4. Now so let's quickly, so that means my flux, rate of flux now can be written as area. The area is 3.14 times 10 to the power minus 4. Okay, so let me clean this up. Now multiplied by the rate of change of flux is now your dB over dt is actually 0.02 minus 0.01. That means change of flux final minus initial divided by the time, which is 34. Okay, so we are going to get 0.01 divided by 34, and this is 2 points, so this is giving us 2.94 times 10 to the power minus 4. Okay, so I'm going to say times 2.94 times 10 to the power minus 4. Okay, so 3.14 times 10 to the power minus 4 multiplied by 2.94 times 10 to the power minus 4 is giving us, so the answer here is 9.23 times 10 to the power minus 8. 9.23 times 10 to the power minus 8. We're talking of induced EMF, so volts. But the question says we should find induced current, okay? So we can now say here that induced current is equal to induced EMF divided by the resistance. According to Ohm's law, V equal to IR, don't forget that. So your EMF here, your induced EMF is 9.23 times 10 to the power minus 8 divided by resistance here is 0.1. Okay, so that would be 9.23 times 10 to the power minus 7 amperes will be the induced current. This is beautiful. Now see another question. In this case now it is a loop. A band of 500 rectangular loops of wire of area 20 by 20 encloses a region of magnetic field which changes from 1.0 Tesla to 0.4 Tesla within 5 seconds. Calculate the induced EMF. The induced EMF still hasn't changed. So my induced EMF is N times this, okay? So let's find the change in this over T first of all. That will give us 1 minus 0.4 divided by the time here is 5. So that will be 0.6 divided by 5. That will give us 0.12, okay? Yeah, 0.12. So my induced EMF now will be N times A dB over dt. So your N here, number of turns here is 500. Your A is area, 20 times 20, that's 0.02 times another 0.02, that's area. And the rate of change of B is 0.12. Okay. Let me write it here, 0.12. And that will give us 500 times 0.02 times 0.02 times 0.12. So that gives us 0.024. So the induced EMF here is 0.024 volts. I think these examples are quite enough. So now that leads us to factors that affect induced EMF. Very important. So induced EMF is affected by the following 4 factors. Number 1, the induced EMF is proportional to the number of turns in a coil. Okay, we should know that. Number 2 is the speed at which the conductor moves through the magnetic field. Number 3, it also depends on the length of the conductor. Number 4, it depends on the rate at which the conductor cuts the magnetic lines of force. Actually, the first 3 is significant. Number 4 is just relating to the first 3. Now, in different scenarios, we have induced EMF. Like in a moving rod, if a rod is moving in a moving rod in a magnetic field, current will be induced in that rod. The induced EMF is BLV. B is magnetic field, L is length of the conductor, V is the velocity. But if it is a loop, we are going to have BAN omega, ban omega. Okay. Now, if it is a rotating rod, that means a rod rotating. In a magnetic field, you have this B omega L squared all over 2. Then if it is a disk, we have this B omega R squared all over 2. Remember, omega there means angular velocity. So we can actually see different questions here. Now look at this. We have calculate the maximum value of the EMF generated in a coil with 200 turns and of area 10 centimeters square, rotating at 60 radians per second in a field of flux density 0.1 Tesla. So just like we have here, your EMF is band BAN omega. Your B is 0.1. The area is 10 centimeters squared. That means 10 times 10 to the power minus 4 meters squared, converting it. The number of turns here is 200, and omega here is 60 radians per second. So I'm with my calculator here. 0.1 times 10 times 10 raised to the power minus 4 times times 200 and times 60. That will give us 1.2. So the induced EMF here is 1.2 volts. Let's see another question. Here we say calculate the voltage generated when 500 tons of wire is rotated. Here now the wire is rotated in a magnetic field of flux density being equal to 0.5 Tesla when its length is 5 centimeter and the speed of rotation is 1 meter per second. Okay, so that's the formula we use. E equal to B omega L squared all over 2. So here my B here is 0.5 omega. We are not given, but we are given the speed of rotation 1 meter per second square. But remember that speed V equal to omega R. So that means omega will be equal to V over R. In this case now, my V is 1. My R here is the length of the wire, which is 0.05. And that will give us 20 radians per second. So I will multiply here by 20 times L squared. The length squared means 0.05 squared. Then divided by 2. Okay. So if we do that, 0.5 times 20 times 0.05 squared divided by 2, that will give us 0.0125. Okay, we're going to get 0.0125 volts as an EMF. Now we see another question. A circuit has an area of 0.4 meters square and consists of 50 loops of wire. If the loops are twisted and allowed to rotate at a constant angular velocity of 10 radians per second in a magnetic field of 0.4 Tesla, the amplitude of the induced voltage is, here we can see this is a loop, so BAN, induced voltage is BAN omega. Your B is magnetic field, which is 0.4, multiplied by the area is also 0.4 meters squared. The number of loops is 50, then the omega is 10. You see, this is quite easy. So 0.4 times 0.4 times 50 times 10, that will give us 80. So here the induced EMF is simply 80 volts. Okay, now look at this. A wire of length 30 centimeters is moved with a speed of 2 meters per second at right angles to a magnetic field of flux density 0.4 T. Calculate the EMF induced in the wire. In this case now, it is not rotating, it just moves. So the EMF is BLV. So your B here is 0.4. Your L is the length of the wire, which is 30 centimeters, that's 0.3 meters. Then your V is the velocity, that's 2. So you're going to have 0.4 times 0.3 times 2, that will give us 0.24 volts. Okay, it's quite interesting. Okay, so here we come to the end of this electromagnetic induction. Thank you very much.